So let's look at an example to end this module. We said in the prior video that you should always include as many factors as you possibly can in a set of experiments. Do you remember why we recommended that? If not, please review the prior video again. In this example, we are going to use 7 factors and the fewest possible experiments. That's 8 experiments. We're going to screen out which of those 7 factors really affect our outcome. So it is a screening design with 8 experiments and a resolution of 3. I could choose more experiments and then go to higher and higher resolutions. But let's see what happens when we start with just 8 experiments and 7 factors. With 8 experiments, we have factors A, B, and C to form a full factorial in 8 rows. The trade-off table tells us to generate factors D, E, F, and G. Now notice that this is a 2 to the 7 minus 4 design. So this design has P equal to 4. These 4 generators can be used to form the columns for the remaining factors in my system. And here's the completed table. I can go ahead and run the experiments and start my analysis. But the whole purpose of the tools introduced in this module is all about checking your aliasing before you start the analysis. Let's go do that. Our 4 generators are rearranged over here. I equals ABD, I equals ACE, and so on. How many words in our defining relationship? 2 to the power of P, and with P equals 4 in this case, that equals 16 words. That's a lot of words to figure out, but let's give it a try. The first few words are easy. Take the rearranged generators individually. I equals ABD equals ACE equals BCF equals ABCG. That's 5 of them. Now we can add to that the combinations 2 at a time. ABD times ACE, and that simplifies to BCDE. The next combination 2 at a time is ABD times BCF, and that equals ACDF. You can prove to yourself that those are the remaining 4. Now we've got 11 words so far in our defining relationship. The next step is to take our generators 3 at a time. ABD times ACE times BCF. That equals to DEF. Try the next 3. So there we have a total of 15. And the final combination is to use all 4 generators multiplied together, and that simplifies to ABCDEFG. So here's our complete defining relationship. Now let's go try and calculate the aliasing for factor A. If we go and do that, we get this very long expression over here. I've highlighted only the 2-factor interactions that are confounded with the main effect of A. I can create this list of aliases for the 7 main effects in my design. This illustrates the tremendous confounding that takes place in the very dense designs at the far right-hand side of the trade-off table. Remember, instead of doing 2 to the 7, which equals 128 experiments, we've done 8. There's going to be a steep price to pay for this reduction in work. Now let's go look at the numbers from the outcome variable and how to continue on with the analysis. And as you'll see, and this is very typical, the analysis goes much quicker than the planning. Here's the code that you can use to analyze this design. Please copy and paste it from the website. We recommend that you always clear your environment from prior work. This is because you might have a variable with the same name from a different analysis. This will avoid any confusion. Build the linear model in exactly the same way as you created the design on paper. First, define the 3 variables that you start with, A, B, and C. Next, generate the remaining 4 factors using the definitions from the trade-off table. When you inspect these variables in the console, you should get exactly what you had on paper. Now, add the outcome values recorded for the 8 experiments. I'm going to take them from the standard order table. When you are ready to visualize your linear model, load the PID package using the library command. You would have installed this package if you had been following prior videos. I will quickly note that R packages are frequently updated. You should check for updates regularly, as demonstrated here. So use the Pareto plot command and let's examine the output. we can see here that factors c, a, and g are significant and have a negative reducing effect on the outcome variable. Factor e is a little smaller, and factors b, d, and f have small to negligible coefficients. Note, however, when we say factor a up here is important, it is really a that is aliased with a variety of two-factor and higher interactions. As long as the assumption is true that those two-factor and higher order interactions are small or zero, then that bar in the Pareto plot essentially represents the effect of factor a. What about the unimportance of small effects down here? They can be removed judiciously. As long as you are confident that when you varied factor b, you did so over a large enough range to affect the outcome variable meaningfully, then you can be sure that this Pareto plot shows that factor b really has no significant effect on the outcome. It is safe to remove it. In other words, we have screened factor b out of consideration. So let's go remove factors b, f, and d for those reasons. By removing these three factors, we've reduced ourselves from 7 to 4 factors, but we've still done 8 experiments. We might as well have done the experiments with only factors a, c, g, and e present. Note, however, that we do not have to redo the experiments. If you refit the model in R with only these 4 factors, you get exactly the same coefficients as before. This is due to the independence property that's built into the model's design. Those of you with a least squares background will recognize that the columns in this matrix are independent, so when you rebuild the model you will get the same results. So there's that. We've essentially found ourselves a system with 4 factors in 8 experiments. We've eliminated 3 unimportant variables as we have learned that they have little effect on our outcome. We have retained 4 important factors that we know affect our outcome. We will see in the following module that we can focus our future attention on those important factors now to optimize the system. So that's the end of this module. For advanced students, I do want to point out 2 other reduced designs. The first is a Plackett-Berman design. The regular trade-off table that we've been using shows that you should do a number of runs which is a power of 2, either 4, 8, 16, 32, and so on. But what if you had a budget, for example, for 24 runs? That's more than 16, but not quite enough for 32. Well, Plackett-Berman designs work well for cases where you have a budget that is a multiple of 4, but not one of the existing powers in the table. So a budget of 20, 24, 28, and so on. I'm not going to go into the details of the Plackett-Berman design, but now that you know the terminology, you can search for more information. The final type of design to be aware of is a class of designs called a definitive screening design, and here's a link that you can use to read up some more information. These designs are a type of optimal design. Let's quickly define the term optimal here. It means that the experiments selected obey some sort of criterion, and they're optimized to meet that criterion. The great thing about an optimal design is that they can be very flexible. For example, if you have a limited budget, you can create an optimal design for a given number of factors you're investigating to maximize one of these optimality criteria to fit your budget. A computer algorithm is used to find the settings for each one of the budgeted number of runs so that the optimization criteria is maximized. In other words, the computer is designing the experiments for you. And there are several of these criteria available. This is where the topic of experimental design quickly becomes more mathematical than this course is intended for. So I'm going to leave you at reading this link for more information, and you can quickly see these modern computer-generated designs have some very distinct advantages. So on reflection, this has been a long module in the course. It is imperative that you work on case studies, and preferably with your own data to solidify your knowledge. This can be a tough topic to grasp, so don't be afraid to watch these videos several times and to ask questions. Working with fractional factorials is a bit like playing with fire. The only way to learn is to burn your fingers. So go ahead, play with the fire, but preferably on a system that has no painful penalty, like making biscuits or trying out recipes for good coffee, or preferably both.